Alright, hello everyone and welcome back to the second lecture for the radiometry. We're going to be continuing talking about radiometric concepts. Probably the one you want to pay more attention to is the concept of radiance. The plain English definition of radiance would be brightness. So we're also going to talk about radiant excitance, but that's not as widely used, so that's perhaps the less important of the two, but I still need to talk about it. So in the last lecture, we talked about flux, intensity, and irradiance. And here's the plain English definition, description of it. So that's the left-hand side of the diagram. So we now need to talk about the right-hand side of the diagram. So you have your flux, you have your intensity. So we talked about what happens to that radiation if it hits a surface. But we also need to talk about what happens if it hits a sensor, in this case your eyes. We need to talk about radiance, or how radiant something is, how bright something is. So we already talked about the concept of point sources, in that yes, if it's a fairly small light source, or if it's a situation where you can ignore the size of the light source, that you can assume a light source is a point source. But look above you again. How maybe it's a small light bulb, but other people might have skylights, or as you see in the photo, a really big light fitting. You can hardly call that a light source, a point source, especially if it's flat. Or it doesn't necessarily have to be big. It can also, you also can't assume something is a point source if the size of the source can't be ignored. For example, your visual field machine, which is used for testing, for example, patients with glaucoma to see how much vision loss they have. Here's a photo of me as a PhD student. You can see me trying to measure the radiance of a visual field stimulus, because that's the size of the visual field spot is very, very important. If you use a standard size 3 spot versus a tiny size 1 versus a gigantic size 5, you will get completely different clinical results. That's kind of part of my PhD, and that's why I have that photo. So in cases where you can't ignore the size of the radiation source, it's just really big, you have to use something else. You can't assume it's a point source. So perhaps you can use radiant excitance, less common, or much more common, we use radiance. So let's talk about radiant excitance quickly. It's rarely used, but what it's basically talking about is, well, the bigger the light source, right? Well, let's say you have a light source. It's emitting, say, 100 watts. If you double that in size, you should send out 200 watts. So you're now factoring in the size of the light source. But you're ultimately talking about flux. As we discussed in the last lecture, flux is not quite as useful as intensity. And for that reason, radiant excitance isn't used as much, because you want to know the density of your watts. Your intensity is a lot more useful. If you can express it in watts per steradian, that is a lot more useful. So, So that basically talks about it. For the reason we discussed in previous lectures, you want to talk about the density, the concentration of your flux, which radiant excitance does not give you. In comes radiance, and yes, the best way to describe it using plain English is brightness. It's more convenient, it's more widely used. What it's saying is, well, if you have a source that has an intensity of, let's say, 100, you double that in size, you get 200. You get a much more intense beam from a bigger light source, or everything else being equal. But note that this formula is incomplete. We'll come back to it later in the more complete format. But let's talk about the area first. So what do I mean size affects the intensity? Here is one torch. You can see that the density of the flux isn't very dense. It's pretty sparse. What if we increase it to 2 torches? So sparse flux, increase it to 2 torches, 3 torches, 4 torches. We're adding fluxes to each steradian to the same area. So now you get a very dense flux. So you have to, when you're talking about intensity from a light source, you have to consider the size as well if you can't assume it's a point source. So here's an example here. Here's Steve. He has a light source that's 1 square meter in size, and the radiance is 15 watts per steradian per meter squared. Steve will receive an intensity of how much from one of these blocks? Well, it's 1 times 15. He receives a 15 watts per steradian intense beam from this block. What if he gets 2 blocks, puts it down? What happens then? Well, there's 2 blocks, each contributing 15 watts per steradian each. 2 times 15, he should be receiving 30 watts per steradian intense beam from these 2 blocks. So you get the idea, you have to factor in areas. All things being equal, bigger the light source, the more intense the beam it will emit. So here's another question. If you do have a light source that is flat against the ceiling, it's not really the case for a light source that's like a ball, for instance. If it's a flat light source, you might notice that the illumination, the irradiance is much better in the middle of the room versus the corner of the room. Why is that? Now, some of you are probably thinking, oh, it's the distance, right? Well, that's part of the story. So now if you look at the simulation here, we are factored in for the distance. If you look at the ball directly under the light source, it's much better lit than the ball that's to the side, even though it's the same distance. So the angle appears to matter in this case. And the reason for that is, well, imagine you have a room with a square light source, a flat square light source stuck onto the wall. You stand directly underneath it and look up. The light source looks square. You then move to the edge of the room, and then you look at the light source. It looks like it looks smaller. The shape changes. I know the actual shape doesn't change, but effectively, from your perspective, it looks like the light source is smaller, and it acts like a smaller light source. So you also have to factor in your angle theta, which is again measured from the normal. So let me show it to you on this diagram here. So here we have our light source, 4 torches. You can see that the density of the flux is very, very dense directly under the torch. But how about to the side at the same distance? You can see the flux is much more sparse. So it's not as the beam that you get obliquely is not as intense. You have to factor in the cos theta. Again, it's measured from the normal. By normal, I mean the surface of the arm of the light source. You always measure your theta from, if this is a light source, you need to measure it from here. This is 0. So always remember to do that. Now, but it only really works for a flat light source. It doesn't work for point source or like a really big ball light, for instance. Because as you can see, with a flat light source, the angle matters, the intensity changes with the angle, but with a point source or like a spherical light source, the intensity is constant because it throws out the flux evenly in all directions. So make sure you consider that as well. So here's the full formula for radiance. It's basically describing how much intensity is produced by the light source for every square meter of the light source, but you're also going to need to factor in the angle of view, which is why we also have a cos theta in there. So to reiterate, irradiance is just talking about how well lit a surface is. People often get irradiance and radiance confused, but remember, irradiance is how lit it is. It doesn't consider the property of the surface. It doesn't talk about whether or not the surface is highly reflective or not. It's not relevant when you're talking about irradiance. So that's why you get the same measurement for the dark and lighter side of the carpet in this case. But for radiance, it is the apparent brightness of a surface measured from a specific direction. It's the brightness. And that changes according to several factors. For example, reflectance in this case. You saw that the carpet is irradiated by the same amount on the darker and the brighter side of the carpet, but the brightness apparent brightness is different for the brighter side versus the darker side, because the brighter side has higher reflectance. Again, remember, radiance is equal to reflectance times irradiance. So if you want to find out more and play with it in the lab, make sure you come to the lab, because I do have some activity to demonstrate that the irradiance changes according to the angle of the light source and angle of view. So, one more thing before we finish up. Okay, so what if we have more than one light, or rather, what if we have more than one wavelength? Let's say, what if we have a mixture of 330 nanometer light, 365, 405, etc.? What happens then? Well, all of them is in watts. As we discussed, radiometry is really only talking about the amount of energy there is. So simple, you just add them together. As you can see in this example here, you just add them all together. Simple. But what if you don't have a finite number of wavelengths? For example, a continuous spectrum, for instance, what do you do in this case? Well, realistically, in this case, you divide and conquer. What you do is, say you have your continuous spectrum, y-axis is how much irradiance there is for each wavelength, which is the x-axis. What you can do is you just divide and conquer. You take the first 5 nanometer band, for instance, and measure how much watt of energy there is. Take the second band, measure how much watt of energy is there, the third one, etc., etc., add them all together. So you can just, that's how it's usually done in real life. Divide and conquer, divide the spectrum into 5 steps, measure the wattage for each step, and they add them together. That's how it's usually done in the lab. So that leads to a question, does the wavelength matter at all? Does it matter? Does it matter if a wavelength is 300 nanometer versus 700 nanometer? Does it really matter? In radiometry, yes and no. If you're just talking about purely in terms of energy, it doesn't really matter. Assuming the light gets completely absorbed and gets turned into heat, it doesn't matter if this light is 300 nanometer or 700 nanometer. If the wattage is the same, the amount my hand gets heated up is going to be exactly the same. So in this scenario, the wavelength does not matter. Only the energy matters. But not always. There are certain cases where the wavelength actually does matter if it's something else. Ionizing, for instance, causing chemical reaction inside of your retina, for instance. In that case, the wavelength does matter. So we will talk about that in the next lecture.